you have this 2D grid, and this is an M cross N grid, okay, and this grid contains these values. I mean, any cell can either be 1 or 2 or 0 or -1, and I'll tell you the meaning of these values. 1 means that that particular cell is your source, okay. 2 means that that particular cell is your destination, and it is guaranteed that there is only one source and only one destination. So there is only one occurrence of 1 and 2. There will be only one source and one destination. 0 means that the cells are safe. -1 means that the cells are unsafe. Okay, so you cannot go into those cells which have -1 in them. Now, the change that is present over here is that if you are at a cell I comma j, then from here you cannot just move right and bottom, but you can move left and up also. So if you are at this cell at any unit of time, you can either move 1 unit right, 1 unit left, 1 unit down, and 1 unit up. So there are 4 different kinds of moves that you have over here. So now the question says that you have been given one such matrix, and then you have to tell me that how many different paths are there, count of different paths which help me to reach from 0, 0, sorry, not 0, 0, which help me to reach from source to my destination. Okay, I want to know how many such paths will be there which will help me to reach from the source to destination. I don't want you to print out those paths for me. I simply want you to give me the count of such paths. Okay, so let us take an example. You had a grid which looked like 1, 0, 0, 0, and then 0, 0, 0, 0, and then 0, 0, 2, and -1. So can you see some paths in this which help me reach from this 1 to this 2? Can you see there are certain paths? I'll talk about time complexity, do not worry, like I'll talk about one over here. So one possible path could be something like this, right, 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 bottom, and then I can move left also. This is one such path. Another path could be right, bottom, bottom, right, and again right, right, bottom, left, this and this. So there can be different paths, okay, that can help you reach from source to destination. So you are simply supposed to tell the count of it. So tell me what change will come if I have to solve this question. How is this question different from the previous problem? So my question to all of you here is that if I simply replace the 2 calls with 4 calls in this question, will my job get done, or can there still be a problem? So an important thing to be kept in mind is, so somebody could have thought something like this. Let's say I had 1, 0, and then 0, and then 0, and 0, 2. Somebody is saying that you go like this, then like this, and then like this, and then come back, and then go like this. Is this allowed? So I would say this is not allowed. Why this is not allowed? Because I would want to add that constraint over here that in any path, one cell can be visited at max 1 time. So you can't visit a cell more than 1 time. In this case, you visited one cell 2 times, right? And you can visit that because here you are able to move in right, left, up, down, all the directions. So it can happen that for some set of moves that you are making, you end up visiting the previously visited cell again. Okay, so I don't want you to do that. Coming back to an approach that some of you quoted, some of you said that I can simply replace this code by making 4 calls at maximum, if that is possible. So what will be the problem with that approach? I want you guys to think of it. So when I have, in the last question, my set of moves were just restricted to right move and bottom move. But here it is right, bottom, left, top, everything. So can somebody think what can go wrong? Revisit, isn't it? Guys, can it not happen that I get trapped in a loop, or maybe I end up visiting the same cell that I had visited again? Like it happened over here, guys, isn't it? It happened quite over here, that when you were here, you took a right move, when you were here, you took a bottom move, when you were here, you took a left move, and when you were here, let's say you take a right move, because you are allowed to take it, now you can again come from here to here. Now again, when you are here, you can again come here, and then you can see that you are trapped in a loop kind of thing, and it can happen in any scenario. Let's say you had a situation like this, okay? So you moved from here to here, from here to here, from here to here, here to here, now again from here to here, and then again you will see that you would get trapped in this loop. So it can happen that you are in a loop going on, and that would never end actually. So how do I get rid of this? How do I ensure that a cell that has been visited doesn't get visited again? Yeah, so there comes the solution. So one of you is saying that, hey, use a visited matrix. So can I use that? I can absolutely use that. So I would somehow want to mark a cell that this cell has been visited. Okay, I want to mark it whether it has been visited or not. So can somebody suggest me how to get that done? How do I mark whether a cell is visited or not? So what is the unique identifier of a cell? How is a cell being uniquely identified? By how many values can a cell be identified? By 2 values, which are I and j, right? Which are I and j. So you can have a Boolean is visited matrix of size m cross n. Okay, so if is visited of, let's say, I comma j is false, it means that I comma j has not been touched, so you can touch it. But if it is true, that means it has already been touched, so you should not retouch it. So I can have this kind of matrix, and you would want to initialize everything initially to false. You would want to initialize everything to false. Now what you are doing, so whenever, let's say, you touch a cell, okay, if you touch a cell, you would mark is visited of this thing as true, saying that, hey, I have visited this. So whenever you are visiting something, you mark that thing as visited, and that's how you will ensure that you will not visit the same cell again. But in one way where it solves this problem, it introduces another problem. Don't you feel so? So guys, think of it in this way, that you had something like this, and there was a 1 over here, and there was a 2 over here, and let's say other values were, let's say you had a -1 here, and all other values were 0, 0, 0, 0, 0, 0, 0. Let's say you took a path which was like this. Okay. Let's say you took this kind of path. So what would you do? You have visited these cells, so you would mark that this is visited true, this is visited true, this is visited true, this is visited true, this is visited true. Now guys, tell me, can there not be another path that contains this cell in it? Can there not be another path? There can be, right? For example, I can have a path that moves like this, like this, like this, and then again visited this. But if you had marked these as true, will this poor path be able to take these cells into consideration? No. So that's the problem. So that's the main thing over here, that when you have, visited something, then the problem that happens with you is that when you mark it visited, then maybe other paths cannot consider those cells again. So some of you are saying use backtracking. So do you see how backtracking can be useful over here? How can backtracking be useful over here? Just think of it in this way, that let's say you started your journey, okay? Let's say you started your journey. Let's say you moved from here to here. So now you somehow explored all the paths that start from here and end here, right? In the process of doing that, you would have marked many cells as visited, right? So don't you think it is your responsibility to mark all those cells as false, is visited of them as false, when you return back to this, so that when you start in this direction, you can reconsider those, isn't it? So if you mark a cell as visited, once you have visited every path that starts from that cell and reaches the destination, you should also ensure that you have unmarked those cells. And how can you do that? You can do that using backtracking. Okay, so I'll just try to give you a visual example of this, which is going to make sense for you. So again, here also I want to consider unique paths only initially. So let us understand how can I consider unique paths. You just think of it in this way. If let's say this was your source, okay, then whenever you are here, what is the maximum number of options that you would have, irrespective of what is your I comma j? What is the maximum number of directions that you can move to? Maximum number of directions is 4. For cells like this, you just have 2 options, and it also depends upon whether a cell has been already visited or not. Okay, so I can say that, hey, if I have to reach from here to here, there can be different paths. The first category of that path is such path where the first move was an up move. Second category is that in which first move was right. Third category is that in which first move was left, and final category is that in which first move was bottom. And anything in this category will be different from this, will be different from this, and will be different from this. Right? This is just like, the point for the previous question. Guys, I think this is simple, right? See, any path that reaches from here to here, for that path, the first move will either be right or left or up or down. So everything, all the paths where the first move was this move, let's say this path or this path. So all such paths where first move was this will be different from all such paths where first move was this or this or this. So you can utilize this thing and then you can solve the problem. So let us take a quick example, okay? So let's say my 2D matrix looked something like this: 0, 1, 0, and then 0, 0, 0, and then 0, 2, minus 1, okay? So if I am somewhere, I can move in these 4 directions. So how will I start my journey? So let's say this is my is visited matrix, and whenever I visit a cell, I mark that cell as visited. Okay, so tell me, from where would you want to start your journey? Here your source is not always at 0, 0, isn't it? Here you have to determine where your source is, and can you determine that? You can very easily do that, right? So you will say that, hey, my source is this particular cell, so you'd want to start your journey from here, right? Now tell me one thing, when you are over here, how many choices do you have? How many choices for movements do you have? 3 choices, right? Because there is nothing on top of it, okay? So the 3 choices are moving left, moving right, and the final choice would be moving bottom. And everything here will be different from here, will be different from here, okay? Now, so if you are starting your journey from here, it means that you have visited this cell, isn't it? Since you have visited this cell, so you should mark it, isn't it? It is your responsibility to mark it, and after marking it, you will move in this direction, and this direction, isn't it, guys? Yes, no? Right? Now tell me one thing, when this function returns, would you want to unmark this? No, you won't want to do that. Why? Because even the other paths where the first move was right or bottom would definitely contain that cell in them. So it doesn't make sense to unmark it. You should unmark it when all these paths are over. Then you should unmark what you had marked. So let's say first I'll unmark it, then I'll call this, this, and this. And when all these 3 calls are over, then the last thing that I'll do before returning myself will be to unmark it. So, okay, cool. So first I made a call in this direction. So saying left means that now you have come from here to here. Okay. So now you are here. Okay. So tell me, what is the first thing that you will do? Whenever you reach a cell, what is the first thing that you do? You mark that that cell has been visited, right? And then you make the function calls, and when this entire thing is over, then you undo whatever you had done. So before returning yourself, you will unmark. Okay. So that way what happens that this cell now can be a part of a journey like this, or this cell can be a part of this kind of journey. That is the reason you have to unmark. Otherwise that cell will never be able to get considered in the paths that start with first move as right or first move as bottom. Okay. Cool. So now you mark this. Now what will be the next thing? Next thing will be to figure out the number of options. How many options do you have here? Can you move right? You can't move right. Why can't you move right? You can't move right because this cell is already visited. Can you move left? No. Top? No. But down? Yes. So at this point of time, you have got one choice, which is to move bottom. Okay. So you would move bottom. Moving bottom means what? That now you come over here. Okay. And when this is over, when this entire thing is over, then since you don't have any other choices to make, so when this entire thing is over, then you would want to do what? Then you would want to unmark, right? So now let us just try to understand. So when you are at this particular cell, let me do this later, it might be confusing a bit. So now I'm here. So now I am at this particular cell. So the first thing that I will do is to mark this cell, and now I will see that how many options do I have. So how many options do I have at this point of time? How many options do I have now? I just have two options, and what are those two options? I can either move right or I can move down, right? So I can either move right or I can move down. See, why I can move right and down? Because these cells are not visited yet and they are also safe cells. Okay, that is the reason I can visit over these. So my first choice was to take a right transition, and my second choice could have been to take a bottom transition. And when both of them are over, then before I return myself, what should I do? I should unmark the cell that I had marked. So can you see, whenever control goes to the parent, the state of is visited is how it was. Okay, so that the next few calls, if possible, could be easily made, right? So now again, here when you say you want to go to right, what would it mean? It would mean that now you have visited this, and now you are over here, right? So now you are over here. So what is the first thing that you will do? You will mark this thing as being visited. Okay. And how many choices do you have here? When you are here, how many choices are there? Again, you have two choices. It's easy enough to understand, right? When you are here again, either you can move one unit here or one unit here. So those are the two choices that I have. So my first choice at this point of time could be to move either in right direction or in bottom direction. Okay, and when these are over, then finally I'll undo, which is unmark this. Okay, so that this thing corresponds to this path and bottom means this. So I need to remove this. That is the reason I have done it. Okay, now moving to right means what? That now it will start looking something like this, where I have visited this. Okay, and after visiting this, now I am here in this cell, so I would mark this thing as being visited. Okay. Okay, now you are here. Okay, you are here basically. So how many choices you have at this point of time? You just have one choice, which is to move upside. You can't go right, you can't go bottom. Why you can't go bottom? Because you have a -1 over there. And you can't go left. Why? Because the left cell is already visited. So at this point of time, when you're over here, you just have one choice with you, which is to move to top. Okay, moving to top means what? That you have a situation like this, and this. Okay, and when this is over, when this function call has returned, then you would want to unmark. Okay, so basically when this is over, this would also be over because it had only one option left with it. Okay, by the way, now when you are here, how many options do you have? You don't have any option. So what should you do? What should you do at this point of time? You should simply return, because if you don't have any option, then this should be your termination condition, because there are no paths that will start from here and reach here if this is the state of your is visited matrix. Are you getting my point? There are no paths that start from that index and reaches the destination if that is the state of your is visited matrix. Guys, this is very important point that I have said, because your ability to visit from I, j to destination doesn't only depend on I, j. It also depends upon the state of your matrix. If the state of your matrix would have been something where, let's say, just both of these were visited, in that case you would definitely have seen that there are some paths through which you can visit destination. But your ability to visit from a cell to destination is also guided by the structure of your isVisited array. So this will return. What will happen when this returns? Can you tell me when this returns, what would happen? It had marked a cell as visited. Yes, it had marked a cell as visited. So what does it always do? Whenever you make a call, that cell is marked, okay, and then when it when it says that it sees that there are no other options, then it will first unmark and then it will return to this. Now when it returns to this, does it have any other call to make? No. So again it will return, and when it will return, it will unmark this, so it will be back to this. Okay, now you will take a bottom move from here. Bottom move means what? That from here you will come here. So now it will start looking like this, right? You have this, this, this and this, right? Okay, what should this be? Should this correspond to my another termination condition where I should say that, hey, this is one possible path? So this is the way you can go on, and this is the way you can end up printing all the paths with right set of answers. But whether we can have multiple sources, no, you will not have multiple sources in matrix. There will be only one source and only one destination, and that is still written on the board. Only one occurrence of 1 and 2. So I think now you can very easily code this out. So now when it comes to printing the paths, you can print the paths by considering those vector of pairs, okay? But let's say the question asks you to simply tell me the count of paths. Can you simply tell me the count of paths? Yes, no? How many paths are there that reach from? Okay, how can you tell that? If let's say this function says, what will this function say? This function will say that the number of paths starting from here till here, if that is equal to n1. Similarly, if this returns n2 and if this returns n3, can you tell me what should the actual answer be that it should return? Should be the sum of these? Yes. Why? Because all those paths are distinct from each other. And what is your termination condition? When do you terminate? You terminate whenever you see that you have reached your destination. Because reaching destination means what? Reaching destination means that now you want to return that how many paths are there which reach from here till here. So from here till here, there is just one path. Okay, from destination till destination, there is just one path that exists. Because you would not want to take any other path, because if you take any other path, you would visit destination twice, which is not allowed. Okay, so whenever you reach destination, you simply return one from there. And whenever you reach at a situation like this, where there are no other possibilities, what should you return corresponding to these? What should you return? You should return simply 0, right? So you can write a code that does these things out for you, and that's how your job would get done. Okay, so I'll just quickly try to write the code for this part. Okay, so let's say there is a function count paths, and it returns an integer, which is the number of unique paths from source to destination. So first you will pass the coordinates where you are at, and the initial value of coordinates will be the coordinates of your source. What will be the another thing that you wish to pass? If let's say this grid is globally given to you, what will be another thing that you would want to pass? You would want to pass the destination coordinates. Yeah, destination coordinates make sense. But do you need to pass the destination coordinates? Tell me. Because you know that the destination has a value of 2 in it. Did you get it? The value of destination in the grid will be equal to 2. So I don't need to actually pass that, right? So yeah, the limits of I and j, which are the m and n declared over here. Okay, so I don't need to pass that if I have that globally declared. I would definitely need that visited 2-dimensional array. This is definitely needed. Okay, cool. So what was my termination condition? When did I terminate? I terminated when I reached the destination. So if I see that my a of I j is equal to 2, what should I do? I want to know that how many different paths are there which reach from 2 to 2, from destination to destination. So what should be I returning over here? So I would want to return 1. So definitely what you are saying is also right if you're having a global count to count that how many paths are there. But if the function is a returning function, not a void function, then you would say that, hey, it makes sense to return 1. It should not just be a crammed up concept. It makes sense. Number of paths from destination to destination is just 1. Okay. Yeah. Tell me, otherwise what should I do? Otherwise, if let's say you were here, what was the first and foremost thing that you did when you started your journey from a cell? You marked that as visited. Very good. So you will mark that as visited. So you will say that now visited of I comma j should be transformed from false to true. Okay. Yeah. After marking it, what are the next set of actions that you would want to do? Now you would want to make as many calls as possible. You would want to make as many calls as possible. And what is the maximum number of calls possible? 4 calls, right? So first call can be there for the right cell, which is I comma j plus 1. Will you blindly call for I comma j plus 1? No, you would call only if you can call. And when can you call? If I comma j plus 1 exists, if it is well within the bound of this grid. Are you getting my point? Can you write a function that checks it, right? And another thing, when it is not visited. Okay, so if you see that I comma j plus 1, you write a function is safe. So this is safe function takes 2 coordinates and checks whether that is safe to be visited or not. So what are the logic that this function should have? The logic should be that this I should be in between 0 to m minus 1, and whatever is this second value that you have passed should be in between 0 to n minus 1. Isn't it, guys? Yes, no? This should be the logic that should stay inside is safe function. But there should be one more logic. Can you tell me that? Yeah, that cell should not have a value of minus 1 in it. So a of I comma whatsoever you have passed should not be equal to minus 1. If these things are true, then only this thing will return true, otherwise this will return false. So can you write this function on your own? Is safe function, right? So if that cell is safe, then I should make a call. Is it? Is it right to say? No. There is something else also that I need to inspect. And what is that? Yes, whether it is already visited or not. And how do I check whether it is already visited or not? By checking this thing. So if this thing and not of visited I comma j plus 1, what does it mean? It simply means that I can make a recursive call in I comma j plus 1 and I can pass my visited matrix. Okay. Now this will return something, right? What will this return? This will return the count of paths where the first move was a right move. Okay. So I need to consider that somewhere, because eventually I want to return the sum of all, eventually I want to return the number of different paths. So for that, I needed to take sum of the return value of this plus this plus this. So let me declare a sum variable which is initially 0, and then I keep adding the return values to this sum. Now the same logic that you wrote for right direction, can you write for left, bottom and top? So the same piece of code will come for left, bottom and top. And what will you return eventually? What will you return? You will return the sum, which contains the total number of paths that are out there. Can somebody think of the time complexity of this? What can be maximum amount of time consumed in this? So what is the maximum number of calls that you are making from any node, from any function? What is the maximum number of calls that you can invoke? 4 calls, right? We didn't do, yes, very good. So somebody pointed it out. Before returning, before you return, what is it that you are supposed to do? You are supposed to unmark whatever you had marked. And how do you do that? You do that by converting visited of I comma j as false. So this was do, this was undo, and these were the function calls. So I would say that those of you who are new to the concept of backtracking, you must try to draw this diagram even further and then see, just observe that how the things are changing. Okay, that will give you a very clear picture of it, and then things will be quite intuitive for you. Okay. Cool. So, okay, tell me, to solve this problem, I needed some extra space of m cross n, isn't it? Yes, no? Can I do it without taking that extra space? See, my purpose is to simply ensure that a visited cell should not get visited again by the same path, isn't it, guys? Yes. Yeah, so that makes sense. So how many of you understand that? That whenever you have visited a cell, so let's say you visited this cell, so it had a value 1 in it, whatever it was. So you simply transform this to -1. Okay. So you transform this to -1, and when this is over, then you transform that back to its original value. Okay, so transforming a cell to -1 means what? That particular path will not visit it again, because you have a logic not to visit according to is safe method. So this is another clever way through which you can save the extra space. So you are tampering the original, but please ensure that here, if you are changing, let's say, so the code would look something like this. Let me tell you, instead of this thing, you will have something like this, where you save the old value of that cell. The old value is grid of ij. Okay, save the old value somewhere, and then you mark grid of ij as visited. So instead of marking it as visited over here, you convert it into a poisonous cell. And now when this entire thing is over, then instead of this, you would want to change the value grid ij to its original value. So what should I keep over here? How do I change it to initial value? By putting old value over here, right? So this way you can save on extra space. Regarding time complexity, I would want you guys to take a thought over it, because at max what can happen, see, when you talk about time complexity, you think of the worst case time complexity. So at max what can happen, that there is a node making call to 4 other nodes at every level. In the worst case, it can happen that every node, although it will never happen, but this can be the worst case which you can consider to get an upper cap on your time complexity. But now you will have to think of that, how much could be the length of this? How much could be the length of this? So can somebody think about the length of this? Yeah, so what would be the maximum length of any path? Total number of cells. Some of you are saying m plus n. Those of you who are saying m plus n, you are thinking that in terms of just moving right and bottom. But when you are allowed to move in any direction, you can have a path like this also, where you visited entire cells if all. So in the worst case, it can go to 4 raised to power the depth of it. And what can be the maximum depth? It can be m into n, where m into n is the total number of cells. So in the worst case, it can be 4 raised to power this. And this is huge. This is just too huge. So generally the questions of backtracking have very smaller input size. So see, that should give you another indication that if you see that a problem has got very small input size, and the problem is such which is asking you to print all possible paths or all possible combinations or all possible subsets, somewhere in your mind your bell should ring that, hey, backtracking has to come into scene over here, right? You can approach, or you can figure out whether backtracking can be applied or not by looking at your sizes of input as well.